Hello, I'm Matthew Balance, and I'm here at DVCon 2015 with my poster paper, Jumpstart Software-Driven Hardware Verification with a Verification Framework. So we're all very familiar with hardware verification. We are typically verifying the IP block from the outside, from its interfaces. And with hardware verification, we have lots of infrastructure in terms of libraries and frameworks that help us be very productive in creating those test bench environments. As we move to the system level, more and more of our testing needs to be done from inside the design by running software on the embedded processor and using that software to interact with the IP blocks in the system. Now, we're actually missing some really key things with software-driven verification, and that is we really don't have the frameworks and reuse methodology that we're used to with hardware verification. In addition, we're running in very resource-constrained environments, and typically there aren't OS services, for example, to help us write good tests. So in this block diagram here, we have our core that the test is running on, and we have our software test with what's typically done is these tests are written with the code interacting with the IP block mixed right in with the test code. So what this paper proposes is that we can boost our efficiency and productivity in creating software-driven hardware tests by adding some methodology and notions that we bring from UVM and bringing those into the embedded software space. So I'll highlight just a couple that are in the paper, and you can read the paper for a lot more detail. So one thing that we bring in is the notion of a component model, where functionality is encapsulated in a component, and there's a predefined mechanism for elaborating that component, connecting it to other things, and then starting the behavior within it. Another aspect that is proposed in the paper is a means for delegating implementation. What this means is that a component knows what it needs, it just doesn't know who is going to provide that resource. So with UVM, we delegate implementation with transactions. A sequence provides a transaction, a sequencer consumes it, the two don't need to know about each other, and you can swap implementations quite easily. Software, of course, is a little bit different in that we tend to interact via APIs. And so the framework being proposed here provides a mechanism by which APIs can be delegated, the implementation can be delegated. This really helps with reuse and modularity and makes it easy to create variants of tests quite easily. The final specific thing that we touch on is logging efficiency. So with a software test running in simulation, efficiency is really key. The more time you spend rendering things and computing things on the embedded processor running in simulation, the less meaningful test activity you'll be able to carry out. So the framework here provides a mechanism for delegating rendering of log messages over to the host workstation. This helps keep the test very efficient. So the end result is we have a very modular test system where we have separated out the test functionality from the, say, early driver functionality, and we have ways of extracting information from the test functionality and channeling that, say, to global checking or channeling that back to the workstation. All in all, what this does is help make it much easier to create test variants and swap in test functionality. So in the hardware space, verification frameworks have been very helpful in boosting test creation productivity, facilitating reuse, and making it easy and productive for users to create good tests. This paper proposes that those same benefits can be seen by bringing those same notions of reuse, encapsulation, and design patterns to the embedded software test space. Of course, this is a very quick flyby of the topic, and there's a lot more detail in the paper. So please go look that up on Verification Academy and get all of the details. Thanks for watching.